Welcome to our video over vibrational damping systems.
The purpose of this video is to inform you of what a vibrational damper is, its real-world applications, and how we may use mathematical models to better understand the effects of vibrational dampers on a system.
What is a damper? Engineering Dictionary defines a damper as a friction device used for controlling damping spring oscillations. What does a damper do? A damper, or a shock absorber, slows down and reduces the magnitude of vibratory motions by turning the kinetic energy of suspension movement into heat energy that can be dissipated through hydraulic fluid. How a damping system works. In the animation on the left, we see how the input force manifests as the rocking back and forth motion of the object. The damper, hanging from the center, absorbs these vibrations, allowing the object to stabilize. The graphical interpretation on the right shows how the magnitude of the force dissipates with respect to time, and how the spring mass damper system reaches equilibrium as the energy is converted to thermal instead of kinetic and potential. One real-world application is what you see on the right, a car known as a lowrider, equipped with a hydraulic lift kit. Electric hydraulic pumps and normal hydraulic cylinders connected alongside the spring of the vehicle's dampening system, shown in the figure on the left, allow for the car to change its height dramatically while not doing damage to the body of the car during its downward motion. While this may seem silly, there are instances where this application is very useful, such as multi-terrain vehicles. Another real-world application is the keys of a piano. With pianos, a damper is attached to a string known as a harpsichord. The damper deadens the vibration of each string as its key is released. This allows for the tuning and individual note playing that makes pianos so pleasing to hear. An example of dampers occurring organically in nature is the human spinal cord. The spine consists of something called invertible discs that are situated between bones of the spine and are made of tough fibrous materials called cartilage. At the center of a disc, there is a jelly-like viscous fluid. Together, the rings and the fluid act as shock absorbers during impactful motion like running and jumping.
What are the effects of vibrational damping? Vibrational damping may reduce periodic motion, such as the mass spring system in the middle. By introducing a damper into the system will return to equilibrium and come to a stop. Whereas without a damper, we know the vibrational motion would continue as seen with Newton's first law, which essentially says that an object at rest will stay at rest and an object in motion will stay in motion with the same speed and in the same direction unless acted upon by an unbalanced force. The damper accomplishes this by absorbing the energy of the system and thereby reducing its amplitude as well as energy to zero. Vibrational damping may also reduce or prevent the unwanted effects of resonance, which is essentially when an object vibrates at the same natural frequency of another object and causes the second object to also vibrate. A good example of the unwanted effects of resonance is the Tacoma Narrows Bridge that was built in Washington in 1940. Essentially, what had happened was that the wind happened to blow at a frequency that was roughly equal to the natural frequency of the bridge. So the bridge started oscillating with an increasing amplitude and eventually got so stretched and distorted that it eventually cracked and collapsed altogether. There are three main components that we should consider when choosing a damper for a given system, one being the damping coefficient. It is ideal to choose a high damping coefficient that will diminish the response by swallowing the energy and therefore reducing the undesired reaction. Another property we should consider is a wide temperature range stability. It is important to have a flexible energy absorption system that can provide reliable and stable damping characteristics over wide temperature range, especially in extreme environments or conditions. Lastly, it is important to consider a damper with a long fatigue life. Essentially, it is ideal to have a damper with a long lifespan without failure. These characteristics can be determined with different types of tests, such as unidirectional, quasi-static, and dynamic cyclic loading tests to establish damper fatigue limit state properties. We have seen many different systems involving dampers within the course of this semester, and we can use these mathematical models to analyze real-life systems as well. One such example we've seen is a mechanical system with a mass, spring, and damper. Here, B represents the damping coefficient and K represents the spring constant. From this system, we can obtain a mathematical model and eventually a solution x of t. To find x of t, first we may use Newton's second law to write our equation of motion. Then we may rearrange our equation to obtain a mathematical model of our system. Next, we plug our values into our mathematical model, and now we may take the Laplace transform of each term, simplify, and rearrange our equation to find x of s. Finally, we can take the inverse Laplace transform of x of s to yield x of t. We have even seen and analyzed more complex systems, such as one with two springs, a mass, a damper, and a step force input, as seen in the system to the right. We may find the transfer function in this system. A transfer function is mathematically defined as the Laplace transform of the output divided by the Laplace transform of the input. To solve this problem, we can first determine a mathematical model of the system by writing down our equations of motion. We can then take the Laplace transform of each equation and then solve for our transfer function using the method of substitution. We can go even further and also find a solution x of t by defining our force P of s to equal 10 over s, since it is a step force of magnitude 10 newtons. Then, using MATLAB, we can find our coefficients and then take the inverse Laplace transform to find our analytical solution x of t.
Thank you for watching our informative video.
We hope you learned more about dampers and how we may apply this knowledge in real-life situations.